Okay, good morning, everyone. Welcome to the last plenary talk of the last day of the UKOA. It's my great pleasure to introduce Kasia Rejzner. She's from the University of York and is going to talk about competitive algebras, measurement, and QRF and QFT. Please take it away.
Thank you. Thank you so much for the invitation to this nice event. And yeah, I guess this probably is going to be the most physicsy talk of the conference, so I apologize about that. So my work is in quantum field theory, and part of quantum field theory that is using operator algebras to describe models. So I'm going to start with introducing the framework of algebraic quantum field theory, where all these things make sense. Then I will talk a bit about measurement theory and how to understand it in that framework. Then quantum reference frames, and then, well, depending how much time I have left, I will go into examples in less or more depth. Okay, so let me start with some very basic things. So algebraic quantum field theory. So here's the idea. First of all, well, it was goes back to Hart and Kasia. Okay, and it started as a framework to describe quantum field theory on Minkowski spacetime, but right now it's applied in a more general setting to consider quantum field theories on more general Lorentzian manifolds. So let's start with that. So let's take M, which is globally hyperbolic Lorentzian manifold. Okay, globally hyperbolic means essentially that M is of the form. Are there any questions? No, I mean, I should say that because this is probably very much out of your well, expertise interest. So please feel free to interrupt me with questions because I don't know what you know. If it's super obvious, then I should probably talk faster. But yeah, just don't hesitate to ask. Okay, so yeah, it's essentially M is R cross sigma, where sigma is a semi-Riemannian. Sorry, it's a Riemannian manifold. Okay, and the whole thing is semi-Riemannian. And then we want to construct quantum field theory on it. And by that, I will mean assigning to regions of that spacetime algebras of observables that sort of represent observables that things that we can measure in those regions. So let's say we have region O in that spacetime, relatively compact. Okay, and to that, I want to assign A of O, which is the algebra of observables. I can measure in O. And now, what algebra? Well, at this point, yeah, so sometimes we do things with general topological star algebras. Well, I mean, it's better if we have some more structure. So ideally, we want to do things with C-star algebras at this stage. So this is C-star algebra more generally. Topological star algebra. Okay.
So if this speaking of M as R times sigma, is it to be thought of as speaking of space and time or not necessarily?
Yeah, if you want to use those words, yes. So R represents time, sigma represents space. And yeah, I mean, there is an obvious example I should have said, which is the Minkowski space now. Which is, M is, well, in 4 dimensions, that's my favorite number of dimensions, because this is like the world, I guess, the one I can observe, with the metric, which is, diagonal with, 1 and -1, something like that. Okay. So that's the sort of running example. Okay, and then there are some axioms that go with it. Yeah, how low can I write so people see it? It's probably up to here. That's it. There's also the video. Okay, so axioms. First one. Okay, so if we have one region instead another region. Okay, so we have a larger system and a smaller system inside, and we expect that we can measure more things in a larger region. So A of O1 is contained in A of O2. Then the next one has something to do with the causal structure. So we are talking about Lorentzian manifolds. So there is a notion of, well, that was already mentioned, space and time. There's the notion of causality, which is very specific to Lorentzian setting. So let me draw a picture here. So we have space, one-dimensional for the sake of this diagram, and time. And causal structure, it means that, well, various, this is that's an example of two-dimensional Minkowski. So 1 minus 1. So various directions in this is actually incidentally also a vector space, will have different behavior with respect to this metric. So we will have vectors which are, with respect to this metric, norm quotation marks, 0, positive or negative, and let me just draw this here. So first of all, there are directions that we call null. So say this is V, and we have that, and this is the metric eta. So we have that V eta V is 0. Okay, this is null. We have things which are positive, so let's call this W. So W eta W is greater than 0. So this we call timeline direction. Okay, and there are things which are either, so let's call it U, and U, eta U is less than 0, and these are space length. Okay, so we have the sort of splitting of things into space length, time length, and null directions, and there is some physics attached to it. So Einstein causality, principle of special relativity, where all this stuff essentially comes from, tells us that things which are in space like separated regions, so say I have O1, 2, O1 and O2 here, they cannot communicate with each other. Why? Because, well, according to special relativity, observers, so us, matter, fields, everything with non-zero mass, is moving, well, to the future within this part of space, which is called the light cone, or the inside of the light cone. Okay, light is moving along null directions and nothing is moving here, which means that there is no way for people who are here or who are here to communicate. So for example, I'm giving a talk here in Belfast and my collaborator is in York and he has no idea what I'm telling you. And he will not find out until the talk is over.
I don't know what look the hour.
Oh, see, this is the not faster than light communication, but fast enough. Um, so some of it is going to be actually about making precise this notion of, well, what does it mean that the measurements here are independent of the measurements here? That for now, this is actually just words. But a sort of crude way of saying it is that, well, in quantum theory, observables are presented by operators. Things that are independent should commute. Okay, so in a very sort of crude sense, we can say that if O1 is space-like to O2, then A of O1 and A of O2 have to commute. So all the operators here commute with all the operators there. And there is another axiom which is important, which has something to do with dynamics. So let me draw another picture. So this is some relatively compact region. And then here inside it, I have a hypersurface, which I again call sigma. If this hypersurface is a Cauchy surface, being a Cauchy surface, it means that it's intersected exactly once by every time-like curve. So it's a time-like curve, time-like. And it's a Cauchy surface. Okay, so if that is the case, then classically, if I was doing classical PDEs, if I have a system which is hyperbolic, means, well, normally hyperbolic would be even better. I have something called the Cauchy problem. So if I set initial values on that surface, so the values of the field or whatever I have in my PD and the values of the derivatives, that should reconstruct the solution in the whole space. Now here I have an algebraic version of that. So if I have a neighborhood N, that Cauchy surface, let's call it N, then the algebra of that neighborhood, well, it would be in general contained in A of O, but here I request something stronger. So A of N is equal to A of O. And this thing is called the time slice axiom. Okay, and well, this thing was called causality. Okay. And there's one more that I want to require. So these are the starts for the basic set of axioms. Usually in a QFT, one requires more things if you have some distinguished states on these algebras, but we don't need it for now. Instead, I'm going to ask for one more property, which is sometimes fulfilled by AQFT models, but it's not part of the axiomatic framework, which is called Hack's property. So this together with Hack's property. So it says the following. So this is something about relationship between the algebras. You can, the algebra of a region and the commutants of algebras that you assign to the causal complement of that region. So let's take the following. So let's take region O. So and inside it some compact region K. So here's K, and then we can take something called the causal complement. Okay, let me make it more diamond-like, then it's easier to draw everything. The dimensions for the causal complement of K is everything which is not in the causal future, not in the causal past of K. So this is K perp. So K perp is the causal complement. Okay, so this is my spacetime minus the sum of J plus of K. So that's the future. Plus of K. And past K minus. Sum J minus. Okay, right, so then I can look at observables that are assigned to regions which are in this complement, and see what happens if I take all such observables. So let's say I have K now in O, and the Hag property is saying that if I take for A, oh, maybe I should have said that. So I have this net structure here. So I have this sort of family of algebras for increasing regions. I can take inductive limit. So A of M is inductive limit of all these A of O's. So I can assign algebras to regions which are not relatively compact just by taking this inductive limit, so growing things until I exhaust the region. And in particular, I can assign the global algebra to M, the whole space. I needed that for notation. So I have some A, which is an operator, I don't know where it is, and I know that it commutes with all B, which are in this complement region. So that if that implies that A is in fact an operator in this region O, let's say this is something larger here, O, then this is Hag's property. So Hag's property says that the above implies that A is in A of O. Okay, so I have two ways of obtaining the algebra of a given region. So one is by this inductive limit construction, so growing things from inside, and the other one is from outside, taking things that commute with everything localized in the causal complement, so sort of shrinking things from the outside. And Hag's property tells me that these two ways of thinking about the algebra assigned to a region coincide. This is important for this measurement story because Hag's property is going to be crucial. Okay, so let's now, okay, and now we have super algebras. If I want to go to von Neumann algebras, I need to specify a state on my algebra A of M, and yeah, it's so usually very straightforward. So typically, well, for the sake of decency, I want the state to be faithful. So they're, yeah, they're very prudent people. So omega is faithful state on A of M. Well, having a state, I can do the GNS construction, which allows me to construct a Hilbert space representation. This is somewhat standard, so Hilbert space representation with some distinguished vector omega. Okay, so I guess, yeah, if I'm working in the C star algebraic setting, I don't need to specify anything more. If I work with topological star algebra setting, so if A is not a C star algebra, but something more general, then this representation would be by unbounded operators. I would have to specify domain, but I'm lazy, so I'll work with C star algebras. So on, and this is C star algebra. Okay, and then, well, this is a Hilbert space representation. And this is some distinguished vector. Such that expectation value of A in this state is given in terms of this Hilbert space inner product and this distinguished vector as follows. That should be pi. Right? All right, so I have this representation, and then for a given local algebra for a given A of O for a region, I can take a double commutant and end up with a von Neumann algebra. So now from that I have a net of Neumann algebras. So M of O defined as the double commutant of A of O representation. Okay. Very good. So that's my setup. And now the question here is, coming back to this, measuring things and so on. What does it actually mean that I have observables and I can measure them? And this seems an obvious question, but it hasn't actually been properly addressed for a long time in the QFT history. So these axioms go back to 64. Now the proper measurement theory for this setting was proposed in 2020. So there's a bit of a gap. So let's talk about measurement. And here I'm referring to the framework and my colleague from York, Chris Fuster, and Rainer Fesch, Leipzig, the paper in Communications Mathematical Physics from 2020. So they proposed how to make sense of measurements in this setting. And okay, well, what does it mean to have a measurement framework? So I'm thinking of a setup where I have a system and I have a probe which I use to measure that system, plain and simple. So what I have access to, what I can actually control is the probe, and the system is what it is. So what I prepare is a state which, by measuring the probe, it should tell me something about the system. So a very basic setup is that, well, both the system and the probe should be quantum field theories, because I believe that the world is quantum and field theory. So I have a net of algebras of the system. Okay, and then I have another set of algebras of the probe. And then what? I mean, the simplest thing is I can just couple them in a stupid way. So I take the tensor product. So they're not interacting. So I take tensor product, a tensor P, and this is U, which is uncoupled theory. Okay. And I can also couple them, and more specifically, I want to couple them in a compact region. So I imagine that there is the time when I start my experiment, there is the time when I stop my experiment, and my experiment is also sort of, finite in space. So there's some compact region where things happen. So there is another theory, which I call C, which is coupled theory. Okay, and the picture is as follows. So there is some region K where this C and U differ. So differ in K in terms of these nets of local algebras. And then this K, well, I can draw the same picture as before. So really wrong. So I have the causal feature of K, causal past of K, something here, which is its causal completion, and everything sits inside some larger space. M. So very bad drawing. So this is M. And again, I have here J plus of K and J minus of K. All right, so I have that set up, and what can I say about it? So first of all, I'm going to use this time slice axiom, so the last one in this list, to compare these theories. So this tensor product and this coupled theory, in the future and in the past. Okay, so if I look at this picture, well, if I take the region, green maybe. So let's first take the region which is M minus the causal past of K. So everything here. Okay, so this is how do I call it? M plus. M plus. This is M minus J minus K. So this region surely somewhere contains a Cauchy surface. So let's call it sigma plus. So by the time slice axiom, I have for any of these theories, I have an isomorphism between the algebra, any of these algebras I assign to that region alone and to the whole space-time because it contains a Cauchy surface. Okay, so there is isomorphism tau plus from in particular the uncoupled. So okay, so these they said these theories, the coupled and uncoupled one, they coincide in this region, right? Because they're outside K. And for this tensor product, I can also apply the time space axiom. So we know that because they coincide in that region, and there's a time space axiom, there's an isomorphism between uncoupled and coupled theory of the whole space, and I can do the same game with a different marker in the past. So I took this, so now I take that. Okay, so this blue one is a minus, which is m minus j plus. Okay, all right. So I have isomorphism now relates things in the past. So this is again a of m to c of m. And this notion of coinciding with the past and coinciding in the future, this is somewhat related to the idea of scattering theory in physics and quantum field theory. So you can think of, well, in quantum field theory, very often you think of scattering experiments. So you have something that, well, you start with a particular theory in the past, or past something happens. You look at what comes out in the future. So if you think of, say, what happens in a typical collider physics experiment in LHC, this is what they do, right? You prepare something in past infinity, which is here, and then scatter, and then look at it in future infinity, which is here. Infinity doesn't have to be too far away. It's the beauty of approximations. That's why physics is what it is, So there's always an approximation where everything makes sense. But yeah, so hence, if I go around with these isomorphisms, so go identify things in the past and then identify things in the future and compare, this map is called scattering map. So here the composition of these two guys, theta, which is tau plus the tau minus the other direction. This is, if I have not been mistaken, this is u of m to u of m, and this is the scattering. Okay. Almost there with the measurement. So the idea now is to use these identifications to specify a state early, so far in the future, and then specify the measurement of an observable late. So prepare early, measure late. So we have the following early. So we have omega, which is a state on A of m, and sigma, so this is my system, and sigma, which is a state of the probe, P of m, and well, I can tensor them, and I can use these identifications to get a state of the coupled view. So this induces through that pullback past, so I use tau minus. This is just a simple tensor product state. This is a state on coupled theory. Okay, and measure late. Okay, so now let's take some probe observable. Okay, and then I can identify this probe observable with the observable of the coupled theory using top class because I'm measuring length. So this is probe observable. This is top class of one tensor B. Again, this is an element of this coupled theory. Okay, and then I can well put these two things together so I can make sense of what it means. Expectation value of the experiment that measures B in that coupled theory in the state I prepared in the past. So, okay, so this is going to be, or putting these two things together. So the tensor thing applied to composed with the scattering morphism because I have both T plus and T minus in the game applied to this one tensor B. Okay, and then I can read off from the setup what can I learn about some system observable given a probe observable B. So for a probe observable B, there is an induced system observable whose expectation value I can measure by using this state. So here's something called induced observable system observable. So let me just write this down. So this would be some operation which traces out the probe. Okay, so this will be a state, or if I apply it to this tensor product, then I have the expectation value of B times A. So it exactly traces up, you know, over this probe factor in the algebra. And this is composed with this prescription for how to relate the coupled theory observables to the probe observables. So this is that. This applied. Okay. Okay, and then so that omega of A is given to with that thing above. So okay. So these are essentially the base ingredients. Now, if you're not a specialist in measurement theory, you might not know what to do with them. But this is just the starting point. This is the starter package. You can take those ingredients and then make sense of, well, various notions in measurement theory. In particular, there is an important question about state update rules. So if I measure something, well, that, you know, the law is that it changes the system, right? Because you're talking quantum mechanics. But the idea is, well, if you have a measurement which say partially traces things out, so you change the state in a sort of controlled way, how does it affect the system, and what do you what do you learn, what information you obtain about the system and how it actually changes what's left, okay? I mean, that's part of the questions in quantum mechanics. And what you don't want to have is for measurements that happen in space-like separated regions to affect each other. So you don't want to have an actual violation of causality. And this is not obvious because the algebra itself, okay, there is this causality property for the algebras, but there isn't the corresponding property for the states. So states are global, states know everything about everyone. So there could be a situation in principle that your measurement would violate causality. However, with this setup and the way that this is designed with the local coupling, that coupling happens only in these compact regions, and all the theories here satisfy the axiom of locality, of causality in that sense. For all these measurements, well, you preserve causality, you cannot really learn about the properties of the system which is space-like related to. And this is not an obvious thing if you talk to quantum information theory. So now you can go and talk to them, and when people talk about collapse of wave function and spooky action at a distance, and that, you know, causality and quantum mechanics are incompatible, they are compatible. The theory you're looking for is called quantum field theory. That it's actually old. But this is the proof of concept that you can do measurement and make sense. Okay. So that was measurement. And then there is also QRF in the title. So this has something to do with the notion of symmetries. Okay, so I made a point that this coupling here is local. So now I want to look at the situations where my background spacetime has symmetries, and there is some group action on the spacetime which induces some group action on my local algebras. So let me make some space here. So last 10 minutes we are getting to the last abbreviation in this title. I really don't like whiteboards. All right. So symmetries. And quantum reference frames. Okay. So what if I have an isometry group of spacetime M and move this coupling region? So let G be a symmetry group. Isometries of M. Okay, so again, the same picture. This marker I killed already. So we have the coupling K region here, and then I apply G in G, and I can move it somewhere else. There is no reason for this to preserve my coupling region. This is G on K. And let's assume that all my nets are covariant. Assume so A are covariant under G. So there is an action call alpha. So for A and A of M, I get alpha of G of A. So this essentially would transform everyone in this picture. So I have the transformation law for the coupling region. I have the transformation law for these nets. So that, when I put it through the machinery, is going to induce some transformation, which takes some induced system observable to another one. So there is some covariance of the measurement scheme. Under G, okay? So what does it mean in practice? Well, let's say we want to measure position in Minkowski spacetime, okay? And yeah, so I need to tell you where, well, Newtonian mechanics, I need to tell you where the origin is and what the basis vectors are, okay? In Newtonian mechanics, I need to specify a reference frame, because otherwise I cannot tell you where I am. Okay? Without any sort of reference, I cannot tell you where I am or where I'm going. So in classical physics, usually this is the data you don't think about, but it's somewhere there in the background. In the quantum measurement situation, I have the exact same problem, because in order for my information about my measurement to be meaningful, okay, I can tell you, well, I measured 6 or I measured 10. But if you don't know what that 10 or 6 means in terms of, you know, my position and my distance to you, this is absolutely meaningless. So I have to specify what reference frame I'm giving my measurement results in. And the fun fact here is that the world is quantum, so this quantum reference, so this reference frame is also quantum. So I need to be able to give labels to these various measurement schemes that are somehow related to another quantum system. So I need to label them using another quantum system. URM. Sorry, I will need 5 more minutes. Is that okay? Okay, and here is the good news. Somebody came up with a precise definition. What does it mean to have a quantum reference frame? And I'm very grateful for that, because that's something I didn't have to do myself. So here is a definition that goes back. These are quantum reference frame with some symmetry group. So red will that's be an average, the same from our joint paper. And again, very recent, 2023. So this is going to be a quantum reference frame with symmetry group G, and here we assume locally compact, second countable Hausdorff group. And for all the intents and purposes, I'm just calling this nice. We have a nice symmetry group. This is the following data. We have U, E, H, and I'm going to write down here what U, E, H are. Okay. Okay, so H, well, I guess you could guess that one. So it's a Hilbert space separable. Oop. Okay, then E is a normalized EOVM, positive operator value measure from Borel sets of sigma. This is a completely different sigma. Sorry, I now realize that. Oh my God, we are just so inconsistent with this notation. Okay, yeah, because spaces are sigma, right? So sigma here is this quotient with H, so closed. Very bad. Closed subgroup, and this goes to V of H. That's when two communities come together. They realize they both use the same letter for something entirely different. Sorry about that. And there is a unitary going to unitaries of H, and this is strongly continuous. Okay, and then there's a relation between the left action of G on this on sigma and induced action on this P of the N as follows, that this unitary transformation acting groups on E of X is the same as E of G acting on X, right? It's natural that action that I have on sigma. Okay, so that's a quantum reference frame. Now, let's say that I have that, right? So I have this whole setup I talked about here. I have this object, which also transforms under symmetry, the same symmetry group G. So what are now the things I can measure? So with that caveat that I need this labeling system, what I actually measure in practice is the joint algebra of that whole business here, and well, this POVM, these observables belonging to the quantum reference frame. So what are the physical observables? So these are invariants. The joint system. So there is some von Neumann algebra of the system. Okay, insert B of H reference. Okay, so this is that data. And then variant under the action alpha, which is the action I have on the system, because all my algebras here are covariant, insert algebra of the reference. Okay, almost there. And this space has actually very different properties than the original net of algebras I started with. So I can think of these observables as they are no longer local observables in this Kasia framework. I can think of them as semi-local observables, which measure relations between local observables and quantum reference. Right? These are semi-local observables. And fun fact, so people got interested in this in string theory, which was part of the motivation me and my collaborators looked at it. There was a paper of Chandrasekaran, Longo, Pennington, and Witten, where they observed that in the sitter spacetime, that was the motivating example, when you take this as the algebra of observables for the sitter, this as a simple clock reference frame, although they didn't use the word reference frame, clock observer, they would say, and this is sort of natural action you have in that context, then from the type 3 von Neumann factor that you usually have here in QFT, you obtain something which is type 2a. Now they were super excited because they could compute entanglement entropies, and this is great. But I think there is a more general structural question to study systems like that and study their algebraic properties, because well, this is actually what we measure, so we should also care. Okay, thank you. Sorry for going over.
Very much. We have questions for Kasia.
What would be in applications, the interesting kinds of symmetry groups that occur?
Good. I mean, it depends where you want to start. You can start with symmetry. Well, you can start with groups you like, and yeah, build those quotients. And I mean, so here you can produce a lot of examples, and you know, so I mean, you get most fun with infinite dimensional groups, and then this is a somewhat non-trivial construction. For the physics examples I have in mind, you want well, you want sigma to be yes, you want G to be the isometry group of your manifold. So for example, for Minkowski, this would be Poincaré, which is actually, yeah, not that great. Sorry, not Poincaré. This would be Lorentz group. Lorentz group is not so good. But in the sitter spacetime, G was R cross SO3, which was good. And then was the action of R, which was the most interesting part. So yeah, I mean, essentially isometry groups of spacetimes. So that's sort of the examples which we can control. Now, even more interesting would be to develop this framework for gauge groups, so infinite dimensional the groups, which is not there yet. I mean, we haven't really generalized it for things that are not locally compact, but that would be the next step. And yeah, for gravity, you know, people talk about the diffeomorphism group, which I think is a bit ambitious. But yeah, these would be examples to try to work.
In this scattering theory picture of the measurements, why are the tau plus and tau minus defined on like all of M?
Yes, because time slice axiom tells you that the algebra of the neighborhood of a Cauchy surface is isomorphic to the algebra of all, right? So you have so you have from the time slice, you have that let's see, I wanted to well, I can formulate it for anyone, but the coupled theory of M is isomorphic to the coupled theory of M plus via time slice. Okay. And here I'm just explicitly calling this isomorphism tau plus, resulting from this, right? Because and on M plus, this coincides with P. Okay. Sorry, not with P, with U, so uncoupled theory, which is the tensor plot. So yeah, so here I'm heavily using the time slice, so I'm heavily using the fact that I can identify any of these algebras in the neighborhood of a Cauchy surface with the global algebra. That's very powerful. I mean, time size axiom is kind of like being topological, but just in one direction.
One final question, Sergio?
Yeah, so actually about time size axiom.
Yeah.
So when I've seen algebraic quantum field theory, for example, in Hobson's book, they don't use this.
Yes.
What? How does it relate to other axioms used usually in algebraic quantum field theory? Why do you guys?
Well, I don't, sorry, I have to admit my ignorance. I haven't read Halverson's book. I should have. But yeah, I mean, time size axiom is a part of the standard Hassler package. So, I mean, for different purposes, you know, people sometimes drop some things. But yeah, I would say a decent algebraic quantum field theory should have causality, Einstein causality, and the time space axiom. You can argue, well, I guess the sort of isotony, so the subsystem one is also good to have. It's more tricky for gauge theories if you want to go to the framework of like chain complexes and things like up to homotopy, then you might want to forget that. But yeah, time size axiom is essentially the statement of dynamics. So if your theory has some specified dynamics, which should better have, then I would, yeah.
Yeah, but so usually when I see some things like, oh yeah, you have some action of the reals, and then that the observables shifted generate each of the whole thing as a sister algebra.
Yeah, this might actually imply time space axiom. Yeah, that is probably correct. And then that's more restrictive. So this is a more general.
Okay, so just further questions to be holding to the break. She's no, so let's thank Kasia again.